So far, we've learned about discrete random variables and continuous random variables, and today we learn about a third kind of random variable called a mixed random variable. Mixed random variables are sometimes discrete, but sometimes they're continuous. If that doesn't make any sense, consider this example. So you observe someone dialing a phone and record the duration of the call. And there's two possibilities. One third of the calls never begin, maybe because no one answers or the line is busy. And in this case, the duration is 0 minutes. Otherwise, with probability two-thirds, a call is uniformly distributed between 0 and 3 minutes. So if we let A denote the event that the call is answered, then with probability P of A equal to two-thirds, Y is continuous, uniform, 0, 3 random variable. On the other hand, with probability P of A complement equal to one-third equals 0, and Y is discrete. So sometimes Y is continuous, sometimes Y is discrete. In fact, Y is a mixed random variable. So what we want to do in this lecture is develop some tools for finding the CDF of Y and then the PDF of Y and the expected value of Y. The key tool we will use is the unit step function. You may have seen the unit step function in a differential equations class, or maybe you're seeing it right now in Principles VE2. If you haven't seen it, you'll see it a lot more. So this unit step function is pretty simple. The function is is 0 up until 0, and then at time 0, it jumps up to 1. In circuits or in signals and systems, the unit step represents an input signal, say a voltage, which is off up until time 0, and then at time 0, it turns on to a DC level. In probability analysis, we're going to use the unit step to model CDFs that have jump discontinuities. Then we're going to find the PDF by taking the derivative of the CDF, but we'll need then to know, well, what is the derivative of this unit step? We can blindly try to find the derivative of the unit step by looking at the derivative piecewise. So looking at the unit step, I take a derivative, and the derivative is equal of 0 is 0 for x less than 0. And for x greater than 0, 1 has derivative 0, so it's 0 for x greater than 0. But what happens at x equals 0? What's the derivative? In fact, the derivative isn't defined. If we think about the derivative as the rise over the run, we have a unit rise at 0 in 0 run. You can think of that as being infinite slope. For mathematicians, this is a big problem, but for electrical engineers, we have kind of a bookkeeping device to keep track of this jump discontinuity. And the way we think about this is that we think of an approximation to the unit step. And the way this approximation works is that it's 0 up until minus epsilon over 2, and then it's a straight line up to 1 at epsilon over 2. we can call this function u epsilon of x, right? And as epsilon goes to 0, this u epsilon of x converges to the unit step. And as epsilon gets small, it approximates the unit step. So this u epsilon of x is is has a derivative, and that's better behaved than the unit step. So to see this, like let's imagine we take a derivative of this function, and here is minus epsilon over 2, epsilon over 2. So this derivative is 0 below epsilon over minus epsilon over 2, and it's 0 above epsilon over 2 because the function is flat uh, outside of the interval around 0. And then in the interval from minus epsilon over 2, right, this function here, the slope is equal to 1 divided by epsilon over 2 minus epsilon over 2. The slope is 1 over epsilon. So in this interval, uh, the slope is 1 over epsilon. And we'll call this function d epsilon of x, right? D epsilon of x is equal to the derivative of this approximation to the unit step. Now that we have this function d epsilon of x, which is the derivative of our approximation to the unit step, we now take the limit of this as epsilon goes to 0, and we define this as d delta of x, right? So this is some very shady mathematics because in fact, in the limit as epsilon goes to 0, d epsilon of x, uh, as epsilon goes to 0, d epsilon of x at x equals 0 goes to infinity. So in fact, this limit doesn't strictly exist, but this delta function is kind of a bookkeeping device that electrical engineers use to keep track of discrete units of probability. It's instructive to look at this approximation to the delta function, this delta epsilon of x function, right, for different values of epsilon. So for example, at epsilon equals 1, it goes from minus 1/2 to 1/2, and the height is equal to 1, and the area under the curve of this function is equal to 1. On the other hand, when epsilon is 1/8, right, this blue box goes from minus 1/16 to 1/16, and the height of the box is 1 over epsilon equal to 8. So the width of the box is 1/8, and the height is equal to 8. And again, the area is equal to 1. So in fact, for all epsilon, the area under the curve of this function is always equal to 1. Because this is true for arbitrarily small epsilon, this function has some very interesting and useful properties as epsilon goes to 0. The first of these properties is known as the sifting property. So if we take the delta function and we shift it to have its peak at x0, and we multiply that by g of x and integrate over all x, right? The integration that sifts out the value of the function g at x0. Since this might seem kind of mysterious, it's useful to work with the approximation to understand what's going on. So for the approximation of the delta function, we imagine for some small epsilon, this is this is x0 minus epsilon over 2, and this is x0 plus epsilon over 2. Here's x, and this is maybe the function g of x, a nice, smooth, continuous function. What's happening here is that we have taken this integral, g of x, delta x minus x0 dx, and we've approximated it with the integral minus infinity to infinity g of x, delta epsilon of x minus x0 dx. And now when we look at this function, we know that this function is equal to 0 for x less than x0 minus epsilon over 2, and it's equal to 0 for x greater than x0 plus epsilon over 2. So in fact, this integral is equal to the integral from x0 minus epsilon over 2 to x0 plus epsilon over 2 of g of x times 1 over epsilon dx. And this value is actually equal to the average of g of x over the interval x0 minus epsilon over 2, x0 plus epsilon over 2. As epsilon goes to 0, this average is going to be equal to g of x0. A second important property of the delta function is that its integral from minus infinity to x is in fact equal to the unit step. To see this, let's go back and look at our approximation of delta epsilon of x. X looks like this, minus epsilon over 2, epsilon over 2. Right, and this function, when we integrate, let's go minus infinity to x, delta epsilon of v dv. Well, it's equal to 0 if x is less than minus epsilon over 2, because in that case, you're integrating over this region here, right, where the function is 0. Right. On the other hand, if x is greater than epsilon over 2, say x is over here, right? Then we're going to integrate the area under the curve from minus infinity all the way up to x. The area under the curve is always equal to 1. And so we see, right, as epsilon goes to 0, and delta of epsilon becomes uh, uh, the true delta function, right? We get 0 for x less than 0, and we get 1 for x greater than 0, right? And in fact, this is the unit step function. Conceptually, the way to think of this delta function is that the function of x, it's equal to 0 for x less than 0, and it's equal to 0 for x greater than 0. But in fact, at x equals 0, it's in fact infinite. And it's infinite in this special way such that if we integrate this thing, and include this infinity, the value of that integral is zero, because in fact it's the limiting case of the delta epsilon of x, which is always area under the curve, under the impulse, equal to 1. If you like to do your math carefully, this is kind of a terrible state of affairs because this is a terrible function that doesn't really exist. However, if you're an electrical engineer, you'll find that this is actually a very practical and useful tool. For example, suppose y is a discrete random variable which is equally likely to take on the values 1, 2, and 3. So the PMF is 1/3 at y equals 1, 2, and 3, and 0 otherwise. Using the delta function, we'll be able to find a PDF for this function. And the way we do that, of course, is we'll next find the CDF. So here is the CDF. 1, 2, 3. And the CDF is 0 up until 1. And then it jumps up to 1/3. Then it's flat to 2. This is something we learned a couple weeks ago, right? A discrete random variable has a CDF. It's a staircase function. And these jumps are each height 1/3. Algebraically, we can write this CDF using the unit step function as CDF of y is equal to 1/3 u of y minus 1 plus 1/3 u of y minus 2 plus 1/3 u of y minus 3. The first unit step kicks in at y equals 1 and it lifts the CDF up from 0 to 1/3. The second unit step kicks in at y equals 2 and the third unit step kicks in at y equals. Now we can find the PDF by taking the derivative of the CDF. And we do that by taking a derivative of each piece. The 1/3 u to the minus 1, it becomes a 1/3 delta of y minus 1, because each unit step has a derivative, which is this crazy delta function, plus 1/3 delta y minus 2, plus 1/3 delta y minus 3. And conceptually, we can draw a picture of this PDF. 1, 2, 3. This PDF is 0 except at 1, where there's an impulse, a delta function, and 2, and at 3. And then there's a convention we have that these weights on the delta function are labeled as the weights of these impulses. It's important to keep in mind that in fact these impulses are infinite, but in fact they're you can have a weight on them so that the integral of this impulse when weighted by 1/3 will be 1/3 and not 1. So this slide just repeats what I just said and derives a PDF that is the sum of these three impulses for a discrete random variable. So finally, it's all summed up in this figure. We can think of this discrete random variable y as having a PMF over here on the left, which has three mass bars at 1, 2, and 3, each with mass 1/3. Or we can think of it as a CDF, where at 1, 2, and 3, there are jump discontinuities of height 1/3, right? Or we can think of it as a PDF with 3 impulses with weights 1/3. These are all equivalent representations of the same random variable. We can also use the PDF with delta functions in order to calculate the expected value. In this instance, we know that we can write the expected value in terms of the PDF as the integral of y times the PDF of y over all y, right? In this case, this is equal to the integral of minus infinity to infinity y delta of y minus 1 over 3 plus y delta of y minus 2 over 3 plus y delta of y minus 3 over 3 dy. And the next step is that we break up this integral into 3 separate integrals, y delta y minus 1 over 3 dy plus the integral y delta y minus 2 over 3 dy plus the integral y delta y minus 3 over 3 dy. And then for each of these integrals, we can use the sifting property, right? Where the first integral is the value of the function that multiplies the delta y over 3 at y equals 1. And the second is y over 3 integral at y equals 2. And the third integral is y over 3 evaluated at 3. And we obtain 1/3 plus 2/3 plus 3/3 equals 2, which is, of course, the answer we expected because a random variable that is equally likely to be 1, 2, or 3 has expected value 2. But the key thing is here that we can do this now using the PDF and using integrals instead of using summations with the PMF. So this slide just repeats what I just did, but with neat and tidy typesetting rather than my crummy handwriting. In fact, what we did for that example of the discrete random variable that takes on the values 1, 2, and 3 can be generalized. So we can have an arbitrary discrete random variable, which at points xi takes on probability px of xi. And now we know that we can write the CDF as a sum of unit step functions weighted by the probabilities, right? And then if we take a derivative of this function, we do it for each term in the sum. And in this case, the unit step derivative becomes the delta function. And we have the equivalent representation in terms of a PDF, right? Where it's the probabilities of the PMF weighted by the corresponding delta functions. When you have random variables where x0 occurs with some non-zero probability q, right? We now have a couple different ways to represent that. So we can have the probability x0, x is equal to x0 is q, or we could have the PMF at x0 is q, or we could have that the fact that the CDF at just past x0 minus the CDF just before x0, the height of that jump is equal to q. And then finally, we can have an impulse at x0 in the PDF. Version D sometimes looks funny to people, but the way to think of it is that fx of x0 is equal to q delta of x minus x0 evaluated at x equals x0. So it's q delta x0 minus x0 equal to q delta of 0. The thing to keep in mind here is that what the delta function is really doing is serving as a bookkeeping device for keeping track of the fact that this random variable x has a non-zero massive probability at x0. Now that we found out that a discrete random variable can be represented as a sum of delta functions, impulses, we're ready to define what's a mixed random variable. And a mixed random variable is one that is, it both has impulses, delta functions at places, and also has non-zero finite values in other places. Now we're ready to go back to this problem we introduced at the beginning of the lecture, where you dial a telephone, and sometimes the duration of the call is 0, and other times it's a call that has some continuous uniform distribution between 0 and 3 minutes. The problem says to first find the CDF, so that's what we'll do. And we have to go back to first principles here, because Fy, the CDF of y, is that probably y is less than or equal to y. And we have to use the law of total probability to say, oh, it's probably y is less than or equal to y, given that the phone call is not answered, times the probability it's not answered, plus the probability y is less than or equal to y, given that the call is answered, times the probability the call is answered. So we know that the probability the call is not answered is 1/3, and the probability the call is answered is equal to 2/3. But these other terms are actually kind of harder to find. The probability y is less than or equal to y given a complement. Well, given a complement, we know y equals 0. So given a complement, y has a PMF with a mass of 1 at 0, and this corresponds to the probability y less than or equal to y given a complement is just equal to the unit step, because it equals 0 for y less than 0, and it equals 1 for y greater than or equal to 0. Now we're ready to tackle the probability y less than or equal to y given a that the call is answered. In this case, given a, y is uniform from 0 to 3, continuous uniform. And so we know that the CDF in this case is equal to a ramp function, climbs straight, and at 3, it's equal to 1. And algebraically, we can represent this as equal to 0 for y less than 0. It's equal to y over 3 for 0 less than or equal to y less than or equal to 3, and it's equal to 1 for y greater than 3. So now we're ready to put all of these pieces together, and we write the CDF of y as equal to the probability y less than or equal to y given a complement times the probability of a complement, which is 1/3, plus the probability y is less than or equal to y given a times the probability of a, which is 2/3. And this is 1/3 times u of y. And this is 2/3 times this function here, probably y less than or equal to y given a, which is just this function up here. Now we can find the PDF by taking a derivative. And so this is equal to 1/3 delta of y plus 2/3. Well, this is kind of a little bit tricky. Right? It's for y less than 0, this derivative is 0. And for y between, its derivative is 1/3. For y between 0 and 3, and 0 for y greater than 3. So the easiest way to describe this function is to show it graphically. Right? Graphically, we have an impulse of height 1/3, and then we have a function over here which is equal to 2/9 between 0 and 3. So this is 2/9 from 0 to 3. And that's the PDF. So something funny has happened here because at the origin, right, we have an impulse and we also have a term that's 2/9 from the continuous uniform part. But in fact, the impulse is infinitely tall, and it smashes the contribution of the 2/9. So uh, so in fact, one way to write this is this PDF of y is equal to 1/3 delta of 0 at y equals 0, and it's equal to 2/9 at uh, strictly greater than 0 and less than or equal to 3, and then it's equal to 0 otherwise. And that's the complete expression of the PDF. Equivalently, you could have written here delta of y, because at y equals 0, delta of y is delta of 0. There's one more step to do in this problem, and that's to calculate the expected value. And we know the formula. It's the integral of the PDF weighted by y, integrated all over all y. And so now the way to think of this is that we have really two separate integrals to do here. Right? We have one which is y times 1/3 delta of y dy plus the integral 0 to 3 y times 2/9 dy. So by the sifting property, um, at y equals 0, y over 3 equals 0 at y equals 0. So this term is 0, and this term gives you 1/9 y squared from 0 to 3, and that's equal to 1. The solution in the text is perhaps more straightforward or perhaps more confusing, depending on your taste. But the approach in the text is to derive the CDF and graphically depict it. And we see that it jumps, and then it's a ramp, and then it's flat. The key thing to note here is that you can find the PDF by just graphically taking a derivative of this CDF. And the way this works is as follows. You just draw your axes and define the CDF. You're like, well, the PDF, the CDF is 0. maybe I'll use a different color here. CDF is 0 up to 0. And then the CDF here has a jump discontinuity. So in fact, there has to be an impulse here whose weight is equal to the height of that jump. And then finally, the slope here is equal to, it's equal to 2/3 divided by 3, which is 2/9. So in fact, we get 2/9 up to 3. And then it's 0 again. So in fact, it's we get it the same answer we got before, and maybe the way it's done in this solution, you'll prefer to the way I did it a moment ago. Okay, this slide just repeats the expected value calculation, just as we did a few slides ago by hand. So it's worth summing up what we've learned here. And what we learn is that a random variable x always has a CDF. And if the CDF is piecewise flat with discontinuous jumps, i.e. it's a staircase function, which I can't seem to spell the word, then what we know is that x is discrete. On the other hand, if f of x is continuous function, then x is a continuous random variable. And finally, if f of x, the CDF is piecewise continuous in pieces, piecewise, but has some discontinuities, then x is mixed. And finally, if x is discrete or it's mixed, then the PDF of x has to have one or more delta functions. Okay, so we might as well do this quiz since we have time here. The key to this problem is sketching the CDF of x. So here's -1 and the CDF for 0. And then at x equals -1, this second condition kicks in. But at this corner point, this is 0. And now it grows with slope x over 4 all the way to 1. So at 1, this function is equal to 1/2. So it grows. Here the function is equal to 1/2 because at x equals 1, x plus 1 over 4 is 2 over 4, which is 1/2. And then at x equals 1, we see that there's a jump up to 1. So something funny happens there. Okay, so now we can answer the questions. The probability x is less than or equal to 1 is just the CDF at 1, and it equals 1. That's part A. Part B, the probability x is strictly less than 1 is the CDF of x at 1 minus. It corresponds to this point down here, right? Because this discontinuity, this jump, right? The jump equals the probability x equals 1, and probably x is strictly less than 1 doesn't include that. And so this is equal to 1/2. And for part C, the probability x equals 1 is in fact equal to the height of that discontinuity at 1, the jump, it's 1/2. And finally, we can find the PDF, right, by graphically just plotting this, taking this derivative. Here's -1, here is 1. This derivative is 0. Then it's a constant value, right? And the height of that constant value is this slope. The slope is equal to 1/2 divided by 2, right? Because the intervals from -1 to 1. So the slope is 1/4. So this is 1/4. And then at 1, we see that there is a discontinuity, a jump, and the height of that jump is 1/2. And so we have to put in an impulse with a weight of 1/2. And just remember, these impulses, even if you put in a weight of 10 to the -6, the impulse is still infinite, and it's always drawn to be taller than all the continuous parts of the PDF. And so this is the PDF of X.